coupon collecting problem, right? You have heard the problem, or baseball card collection. There are n types of cards, right? So you buy a cereal box, it definitely will have one type of card. So then you eat all the cereal, then you buy a second cereal box, it will have another card. But it's possible that the card in the second box may be the same as that in the first box, in which case you wasted your money, right? So the question is, you have to keep buying the boxes. So the third box may have a different type of card, so that's good. Now you have two cards. So the question is, how many boxes should you buy so that you have one card, at least one card of each type? That's the problem, right? Okay. So we will start with a problem that, so I'm going to somehow connect this, a couple of ways to solve this, but the way I have seen is also to connect it to something what we have studied, Poisson processes or Poisson arrivals. Recall, so in time, things are happening, right? So this is when you buy the first box arrives, or the first coupon arrives, right? Sometime instant t1. So here you can think of as, so then this is the second arrival, right, t2. And if I call this to be tau, this is the tau is the time to first arrival. What is the distribution? This is a random variable because we don't know when tau is going to be. So what is the distribution of tau? Anybody remembers? All right, so the argument goes like this. What is the probability that the first arrival happens beyond some time t? That means the number of arrivals in 0 to t is zero, right? Because the first arrival is beyond t. That means there is nothing in 0 to t. That much is crystal clear, right, by logic. But remember, we say something is Poisson. The number of arrivals in 0 to t equal to k is e raised to minus lambda t to the power k over k factorial. This is what we mean by Poisson process. We can write this as x of t. If you, the number of arrivals in some interval t, k, that then the number of arrivals is equal to k, is given by the Poisson distribution whose parameter is proportional to the duration you are looking at. We went through all this. So if the number of arrivals equal to 0 is from here, you put k equal to 0. So that's going to be e raised to minus lambda t, right? So of course, on the other hand, this side you can write it as 1 minus probability of tau less than or equal to t, right? But this is 1 minus f tau of t, but this is e raised to minus lambda t. So f tau of t is 1 minus e raised to minus lambda t. You take its derivative, you get lambda e raised to minus lambda t, right? For t positive. That means this is exponential. We went through all this. Any questions on this so far?
Tau, you know, tau is just time to first.
No, don't confuse with this t. So So saying that, so look at it, tau is the first arrival, right? We don't know where the first arrival is. So if I pick up t here, saying that tau is beyond this t, right? Is forget about this thing. If I pick up my t anywhere, saying that the first arrival is beyond this t, says that there must be nothing here. That's all I'm saying. That's all this statement says, right?
So tau is just the variable for first.
For it's a random quantity, right? It's a stopping time. It's the time it takes for the first arrival. So first arrival, if it exceeds t, there cannot be any arrivals between 0 and t. That means the probability of the first arrival exceeding any t is e raised to minus lambda t. But this is 1 minus probability of t less than or equal to t, 1 minus the distribution function. And so FTT is this, and you get the density function to be this, right? So, so let's in the so let's assume n Poisson processes. So these arrivals of these coupons, we will we are going to we are going to associate with the Poisson process. So this might be, for example, the kth coupon. So this is the arrival of the kth coupon. So this is this time index. I'm going to write it as this is the first arrival. This k is for which process, which type of coupon. This one is saying that this is the first arrival. If I put a 2 here, what does that mean? Second arrival. So you can see if you now you can draw a picture. Maybe the first time, let's say this is tk1. That means or let's say t21. That means the second coupon arrived. Then it could be t31. The third coupon arrived. Then it could be t22. Second coupon again arrived. Right? You buy and go buy a cereal box. It happened to be something you have seen. This could be t23. That means second coupon again arrived. That's useless to you. You are trying, so this may be t11. First coupon arrived. And etc. This may be tk2. This may be, so you start counting. You see, I see a coupon here that I want. I see a coupon here. So this is 1, this is 2. Then I see a coupon here. I got 3 types of coupons, right? I see here n1. So this may be your n. That means by this time I have collected n minus 1 coupons. And then I see something else happens. Let's say this is some ti1. And I see that this coupon was never came. So I have my nth coupon, right? And I am interested in this time. So this we will call it some sort, then I stop because so this is a stopping time. So another random variable of interest is in lot of phenomena, stopping time. We know it is going to happen, but we just don't know when, right? So Brooklyn Bridge, right? An accident is going to happen, but we don't know exactly at what time, right? Or a specific highway, or any of you having, most of you having your first kid, right? Of course, you have to get married, I would think, right? So that's a stopping time, right? Somewhere it's going to happen, but we don't, it's a random variable, right? So we are interested in this random variable. That's when, how long does it take to collect, you understand now, how long does it take to collect one coupon from, but you see, remember, coupons are not coming, nobody is going to throw you coupons in one by one. It comes in some fashion. So T is what? The maximum of, hello? Oh, so we are making use of things which we studied earlier now. Maximum and minimum. Remember this notation. This is the time it takes for the first coupon to show up for the first time. Second, but this is unfortunately they are not, as I said, they are random variables, so they come whenever they come. But each arrival is what? That's why I did all that stuff. Each of these random variables, let's assume that each of these coupons have nothing to do with each other. So they are all independent processes. So these random variables are independent, but we know their distribution, which is what? Exponential, right? So let's see. So we want the distribution function of, so we are back to probability now, right? So this is a stopping time. So what is its PDF, right? So this is t is given to be maximum of t11, t21, etc. tn1 less than or equal to t, right? So distribution function is by definition random variable less than or equal to t. Now if remember we went through this, if maximum is less than max of x comma y is less than t, then x is less than t, y, each of them has to be less than t. So this is the probability of t11 less than or equal to t, t21 less than or equal to t, etc. tn1 less than or equal to t, right? Now these are independent. Because each coupon in each serial box is all randomly shuffled and arriving, right? Or the processes are independent processes. So they arrive when they arrive, right? So this is the product of t11 less than or equal to t, probability of t21 less than or equal to t, etc. pre of n1 less than or equal to t. Each of them is what? Anybody? Exponential. And they all, let's assume that all these processes are identical parameter we to start with. So each of them is of the form, this is the ft1 of t. If so all of them look the same, so you don't need any subscript. And so consequently there will be how many of them? N. Right. And each of them we know the form. What is it? 1 minus? 1 minus e raised to minus lambda t to the power n, right? For t positive. So you see, we found the distribution of something quite complicated. So of course we can find out its density function. This is going to be n what is it? Isn't it this? Yes? So that's the density function. Ooh. So on the average, how long does it take to collect all coupons, right? So again, suddenly from the stochastic processes, we went to probability. That's why everything is, this is a good illustration of what is going on. So to do this, this is a non-negative random variable, right? So let me draw the density function qualitatively. Look at here. When t equal to 0, what is the value? Anybody? T equal to 0, this is 1, this is 1, 0. T equal to infinity? Look at here, this is going to be 0. So it is 0 here, 0 here. So it's like this. Right? It has to go up and do something like this, right? This is the distribution of FTT, right? So it's a the random variable exists only for positive values of 0, and it is 0 otherwise, so for t less than 0. That's clear, right? So for such random variables, the expected value of so look at this. X is a non-negative random variable. That means the density function is 0 if x is less than 0, like there. Then expected value of x is what? X fxx dx, right? 0 to infinity. So I can write this as, can't I write like this? I don't know whether you have seen this. Of course, you have seen this much, right? X can be written as integral 0 to y x dx, dy, right?
Yes.
So look at how I am integrating here. Now I have y here. Look at here. Y is integrated from 0 to x. So y is integrated from 0 to x. Right? Y is integrated from, and x is integrated from? X is, so I am integrating in this region, right? So let me integrate in that region, but I am going to take a strip like this. So I am going to rewrite this integral as x goes from where? Y to infinity, right?
Yes.
And y goes from?
0 to infinity.
Okay. But what is this quantity?
Uh,
1 minus
1 minus f1, fx1.
That's this, isn't it? So if you want, you can write what you said, right? So this is also a useful expression. Right? Y is a dummy variable, so I can write it like that, right? So let me do that here. This is a positive random variable. So this is the probability of t greater than t dt. Right? But probability of t greater than t is somewhere here, right? So this is integral 0 to infinity. Look at here. Probability of t less than t is this. This is this, right? So probability of t greater than t is what? 1 minus this quantity, right? Let's hope I can do this. Let's see. dt, right? Now I'm going to make the obvious substitution. X equal to 1 minus e raised to minus lambda t. So dx is going to be lambda e raised to minus lambda t. Right? Yes? dt, right? So which is lambda multiplied by 1 minus x dt. So dx by x, 1 minus x is lambda dt. Yes? Did I make a mistake? Because this quantity from here, e raised to minus lambda t is 1 minus x, right? So I substituted for that. So what happens to the limits when t is 0, x is what?
0.
Okay, right. And when t is infinity, x is 1. This one is here, minus x to the power, this whole thing is x. So x to the power n. And dt is, so 1 over lambda, right? I'm sorry, dA, we have dx, what is this? dt, right? So dt is 1 over lambda dx over 1 minus x. Anybody knows how to cancel this? What do you get? 1 minus x over 1 minus x and over x. This you should know, right? High school, right? You're right. So that's 1 plus x plus right? Because you multiply this with this, you get this. You can certainly integrate that, right? So that's going to be, integral is what? X to the power k over k, right? Sigma k equal to 0 through, I mean, the integral will turn out to be, integral of 1 is x, 1 over lambda. Then you have x plus x squared by 2 plus xn over n, 0 to 1, right? So the answer is 1 plus 1 over 2 plus 1 over 3 plus etc. 1 over n, right? You must have seen this result. What happened to lambda? There was a lambda, right? And anyone knows what happens to this series? It converges or diverges? Math major. What happens to this series? 1 plus
High school.
all right, another high school. Right. If you go all the way to infinity, what's the answer to this? Anybody?
2 minus 1 over n plus 1.
If I go to infinity, anybody? The answer? What is it? Huh? I'm just asking, if you add up all the numbers up to infinity, what do you get? Give me a number. 2? What are you saying? Did you say 2? If you said 2, I'm going to fail you. Right? That's a hint, right? This, you must have heard this, this series is so peculiar that if you add up all the way to infinity, it blows up. It doesn't converge. But you must have seen this, right? So the question is, how this is log, natural logarithm. So maybe just a log n, right? I think it's just. Okay, so this blows up as log n, or more accurately, this minus log n is a constant. What is this constant? Anyone? This class seems to be you just never went to school. I mean. So let me just check the value. Hold on. Yeah, so the theorem is that series minus log n converges to gamma, which is 0.57372, etc. Euler's constant, right? All this is there in the notes, etc. Okay. So the whole point is, remember here, of course, you can see, right? If n increases, this blows up, but the difference is a finite quantity. That's the interesting thing. So you say that this series blows up like log n. So if you substitute it here, approximately we can approximate it as gamma. So this series is gamma plus log n, right? Approximately. So if you want an answer, this is a gamma plus log n 1 over lambda. And if I multiply and divide by lambda, I can write this as alright, so why did I multiply and divide? Remember, there are n processes going on. So if you consider x of t as the sum of the processes, x of xit, you know that this is Poisson with parameter equal to sum of the parameters. Each process has parameter lambda. So this is n lambda. And if you want to call n lambda to be mu, so this expected value, which is the time it takes to collect all the coupons, you can see the nature of the issue problem here. It takes a long time. You must have heard that, right? So in fact, the time increases as n log n when you compare it with respect to the average value of the total process. So there is a correction factor which is also not insignificant, especially if n is large. Right? So this is one of those problems where collecting 10 coupons and collecting 20 coupons is not double the time. That's what you can see, right? It's much more complicated than so everything the time increases as in the logarithmically. But it's better than increasing a square, right? Logarithm is weaker than square, right?
From the start, we took lambda as the constant. That lambda should depend on.
No, hold on. Lambda is for each process. So now, if you don't want the n, take it out. I was saying that if you now want to rewrite in terms of the total process, which is the process is, remember what you are observing is the collection of the whole thing. You are not seeing one of them coming in. So what you see here, if you want to, this is going to be x of t. It happened, this may be from x1, this may be from x2 and so on. So its average value is mu, that's what I'm trying to say. So if you, hold on, if you want to write it in terms of this expression is correct, right? All right, what is the question?
From the start we took lambda as a constant for distribution. That lambda, for particular this experiment, that lambda should have some constant, it should depend on something.
All right, so if you want to make it more complicated, you can say that my lambdas are different here. So then everything will get, see remember, then this will all get very complicated because each will be lambda i's and then this won't be n, there will be a product here and all that stuff, right? So that's good. You can't even solve the simple problem. Idea is you put it in such a way so that at least in a special case you can see the degree of difficulty involved. So if so in other words, the time it takes to collect the coupons increases logarithmically. I mean, it's very difficult to see by just staring at the problem, right? So this is one way to, so we are making use of what we learned to address new problems, right?